Let's do some examples of application of the root and ratio tests. Let's do this. The first one, we have a series that is 1/2 plus 1/3 plus 1/2 squared plus 1/3 squared plus 1/2 to the power 3 plus 1/3 to the power 3, and so on. By now, we have already spotted the pattern, right? So we have 1/2 and 1/3 to the power 1, then 1/2 and 1/3 to the power 2, then the power 3, 4, and so on. So that one we have figured out. The second, let's leave it for a moment. Let's focus on the first. The second one, it just looks like everything is a scramble, right? But we will get to that one in a moment. All right, so the first challenge with the first one, although it's very clear what's the rule, and we can tell what's the next term in the sequence, writing down the general term of the series is not so easy. So, well, let's start at 1. Okay, but what is AN? So in this case, AN, if we look at the series, what we see is that it's different depending on if we are at an even or at an odd index. Okay, so that gives a clue that we need to consider two cases. If n is odd, or if n is even. Okay, first of all, we are writing down the general term of the series, because if we don't do this carefully, then writing down the root or the ratio tests, that's going to be impossible. Okay, so first things first. Now, once we have this written, if n is odd, so let's look at the terms. So this is the first one, second, third, fourth, fifth, sixth, seventh, and so on. Well, eighth. Okay, so we see the odd ones are always 1/2. Then to some power. And then the even ones are 1/3 to something. What we are seeing here is that whenever the term is even, okay, the second, the fourth, the sixth, the exponent is half of the term. Okay, so if we are at term 4, the exponent is 2. The sixth term, the exponent is 3. Eighth, the exponent is 4. So we have here that I wrote something. So we take n and we divide by 2. So we have that on the first, the exponent is 1. On the third, the exponent is 2. Fifth, the exponent is 3, and so on. So this is basically half of the next term in the sequence. So it's n plus 1 divided by 2. So this is our general term for the sequence. Okay, if we want, we can write it. We could also go ahead and write it as 1/2 to the k plus 1 for k equals 0, 1, 2, and so on, or 1/3 to the k, 0, 1, 2, and so on. Okay, here we would be writing n equals 2k, here n equals 2k plus 1. All right, that's what they do in the book, actually. But I think it's more confusing, so we won't be doing that. Now, once we have this, we can write an plus 1 over an. But then we need to consider the two cases, if n is odd and if n is even. Okay, I'm going to need more space, so let me, there we go. So if n is odd, okay, then we are dividing by an odd term. When we are dividing by n is odd, here we have 1 over 2 to the n plus 1 over 2. We just look at the formula, n is odd, okay? So it's of this form. So I put it here. And then if n is odd, n plus 1 is even. So 1 over 3, and then instead of n, I put n plus 1, which is even, divided by 2. And now if n is even, then I'm divided by 1 over 3 to the n over 2. And in this case, n plus 1 is odd. So 1 over 2 to the n plus 1 over 2. And that's it. Here we can simplify it. So this is 2/3 to the n plus 1 over 2. There we go. And the second one is 3 to the n over 2 divided by 2 to the n over 2 plus 1. Okay, so we can, yeah, I knew I needed a space, but I didn't think I would need so much space. So we can write this as 1 over 2, 3/2 to the n over 2. And that's it. Okay, so now that we have this computed, we can think about what is the limit, or what is the lim, the lim sub. Now, looking at this, what do you think? Is there going to be a limit or not? I see two very different subsequences here. One for the odd terms, the other one for the even terms. And they don't seem to have the same limit, okay? Because 2/3 is smaller than 1. So when we raise it to power n, that's going to go to 0. And 3/2 is bigger than 1, so it's going to go to infinity. So we have two different subsequences here. And actually, we have a lim that is given by the limit of 2/3 to the n plus 1 over 2 as n tends to infinity, which is 0. And we have a lim sub which is the limit of the other subsequence, the even terms, 1/2 of 3/2 to the n over 2, which is infinity. So the lim, we don't care. That's not involved in the ratio test. And getting infinity here, this means the ratio test, this is bigger than 1, definitely. So the ratio test is inconclusive, okay? So all these, we could think all this work for nothing. Okay, so we need to continue because maybe the root test actually works. Let's see. Again, when we compute the nth root of an, we need to consider two cases. Okay, depends on if n is odd as before, or if n is even. By the way, in the book they do it a little different. As I mentioned before, they do this type of conversion. And if you read the example in the book, you will see that here, instead of n plus 1, they have a different quantity. It's because of that, okay? But you can go back and forth. I will just not do it to not create mess. Okay, so if n is odd, I have, let me copy this somewhere so we can, there we go, have it as a reference. So this is, if n is odd, this is 1 over 2 to the n plus 1 over 2n, okay? And then if n is even, this is 1 over 3 to the 1/2. That's it, because the n and the 1 over n cancel each other. So this is 1 over 2 to the 1/2, so square root of 2 times 2 to the 1 over 2n. And that's it. We just need to see now. This I don't need, so I will just delete it. So in this case, the lim inf and the lim sub what are they? So again, here we see two different subsequences, the odd and the even terms. The odd terms, they converge because this term here is going to lose influence, okay? As n goes to infinity, this becomes 0, 2 to the 0 becomes 1. So this converges to 1 over square root of 2, and this is always 1 over 3 to the 1/2. So those are different limits. Let me write it as square root of 3. So which one is bigger, square root of 3 or square root of 2? Square root of 3. So if that one is bigger, the reciprocal is the smallest. So the lim inf is 1 over square root of 3, and the lim sub is 1 over square root of 2, which is less than 1, because the square root of 2 is bigger than 1, and therefore it converges. Okay, here we should say by root test. Okay, so we saw the ratio test was inconclusive, but the root test actually shown convergence. And this is part A. So we still need to do part B here. So let's figure this one out. In this case, when we look at it, it's clear that all of them are powers of 2, right? So this is 1 over 2, 1 over 2 to the 0, 1 over 2 to the 3, 1 over 2 to the 2, 1 over 2 to the 5, 1 over 2 to the 4, 1 over 2 to the 7, 1 over 2 to the 6. So it looks like they are completely scrambled. But actually, no. So when we look at the positions, we see that the odd ones are in place. Okay. So that's already something. And then we only need to figure out the even ones. So in this case, an is going to be 1 over 2 to the n if n is odd, okay? And then something if n is even. So what is that something? Well, it's definitely a power of 1/2. But then for n equal 2, we have an exponent of 0. N equal 4, we have 2. N equal 6, we have 4. N equal 8, we have 6. So it looks like every time we are taking 2 units out of n. So we have 1 over 2 to the n plus n minus 2 if n is even. All right, and then with this, we can already write down an plus 1 over an. Again, this depends on if n is odd or even. So let's see. If n is odd, then the denominator is going to be 1 over 2n. 2 to the n. And then the numerator is going to be 1 over 2 to the n plus 1 minus 2. And then if n is even, I have a denominator 1 over 2 to the n minus 2 and a numerator that is 1 over 2 to the n plus 1. All right. So let's simplify this because, I mean, they are powers of 2, right? It shouldn't be that difficult. So here we have 2 to the n divided by 2 to the n minus 1, which makes 2. And the bottom one is 2 to the n minus 2 divided by 2 to the n plus 1, which makes 2 to the negative 3, 1 over 8. All right, I think this is very clear. This means the lim sup of an plus 1 over an is going to be 2, which is better than 1. So the ratio test is inconclusive. By the way, the lim-inf, although this is not important, but the lim-inf is going to be 1 over 8. Okay, but this doesn't affect the ratio test. By the way, because the lim-sup and the lim-inf are different, that means there is no limit for an plus 1 over an. But anyhow, let's see the root test. Maybe it works. So with the root test, well, actually this one is quite straightforward. Let me copy this so that we can refer to it. So we have to take the nth root, but because it's already a power n, we are all set. And then the other one is 1 to the 1 over 2 to the power 1 minus 2 over n. If n is even, if n is odd. All right. So we are good to go. Now something nice happens here. The lim-sup in this case is equal to the lim-inf. That means there exists a limit of the sequence and the limit is equal to 1/2. Okay, notice here the 2 over n as n tends to infinity disappears and we get 1/2 just as before. Okay, so regardless of odd or even, they both converge to the same thing. So we are good. Okay. But most important, because 1/2 is less than 1, then converges, well, the series converges by the root test. Okay, so we have seen the two examples where the ratio test was inconclusive, but the root test was actually able to say something. We will see in the next video that actually that is always the case. The root test is a bit better than the ratio test, and it sometimes allows to say something more when the ratio test is inconclusive.